clock is counting. It is well known in this community that proper knowledge of GNSS transmitter antenna patterns is pivotal to precise positioning, to precise orbit determination, and precise clock determination. In that context, manufacturer calibrations of those antennas are pretty important. Last but not least, that has been shown by the Galileo calibrations, which also provide the proper chance to calibrate, to contribute to the realization of a GNSS-based TRF. Now, how is the situation for GPS? Over the years, and I'm really talking about a full decade, the GPS providers have step-by-step released piecewise information on the antennas of the GNSS, of the GPS satellites. We currently have 4 different blocks of antennas for which antenna information has been released. The information is pretty inhomogeneous, other than for Galileo, that has to be emphasized, but at least we do now have, since almost 1 year, a complete set of antenna calibrations for Block IIR, IIR-M, IIF, and Block III satellites. IIF was the latest addition. 10 years after the first launch of the IIF, we finally got the antenna data. The nice thing about the manufacturer calibration is that those provide band-specific data, which is nice for those that use uncombined processing approaches. However, I must say that there has been a focus on gain pattern information, which is mostly useless in our community, but highly favored by the space science community that uses that to compute link budgets for spaceborne missions. Another disadvantage is that the phase calibrations, which are included in the Lockheed and Boeing datasets, lack a proper documentation and require extensive creativity and pre-processing. They also refer to an unknown calibration point, which I will discuss later. On the other hand, the data are complemented by phase center offset relative to the center of mass, published by NGA, the National Geospatial Agency of the US. However, merging these data sets tends out to be a bit difficult. In order to explain the terminology, basically in the IGS antenna models, we are used to describing phase variations relative to the center of mass of the GNSS satellite by first accounting for a so-called phase center offset from the center of mass. That's one piece of information, and then referring the phase variation to that phase center. The phase center is conceptually a point for which the deviations of the residual phase relative to a sphere around the phase center becomes minimal. That sounds easy, but it's harder to implement in practice, as I will shortly show. However, the manufacturer calibrations refer to a mechanical point realized in the anechoic chamber, the so-called calibration reference point, that has nothing to do with either the phase center or the center of mass, and that means it's a bit difficult to get this information together if nobody tells you where that calibration point is. I was going to talk about phase center definition. I said it's the phase center is conceptually the point for which the phase variation relative to a sphere around that point are minimized. However, how is that minimization done? First of all, it is only done about, say, the relevant part of the antenna beam, the one that is basically the Earth coverage zone. Secondly, the question is on which type of grid we do that minimization. It's a least squares minimization on certain sample points, and it turns out by reverse engineering that Lockheed Martin has used basically an equidistant grid in azimuth and boresight angle at 2 degree spacing and equally treated each sample point. That means the weighting puts a heavy weight on the boresight direction. It flattens the pattern in the boresight direction, but creates a kind of ring around it where the amplitude is higher than necessary. If we would use a kind of isotropic weighting with isotropically distributed sample points as shown in the right, the overall pattern would be flatter, but we would get the famous red nose in the center. So it's important to understand what the convention is, but by reverse engineering we were able to find that out. Now, looking at the resulting patterns, this plot of 4 by 2 patterns shows from left to right the 2RA, then 2RM, then 2F, and then block 3 patterns. The top one are the manufacturer patterns, the lower ones are patterns observed by Technical University of Graz. In this case, it's the ionosphere-free combination of L1 and L2. And you see that they have a striking similarity. The patterns of individual blocks are quite different, even so the antenna design looks very similar. It's always the combination of an outer ring of 8 helix elements with an inner ring of 4 elements that is twisted by 45 degrees. But the resulting pattern, due to different phase delays between the individual elements, gets different. But it's nice to see that there's a very good overall match. Regarding the PCOs, the situation is more difficult. It needs a bit of creativity, and I call it red magic here. We have a problem that we don't know exactly what the meaning of the NGA PCO information is. On the other hand, the phase patterns that you got from Lockheed and Boeing refer to an unknown calibration reference point. Now, by assuming that all patterns or all PCO estimates have originally been based on that equidistant grid, we can reconstruct out of the manufacturer phase patterns the corresponding phase center. Secondly, if we assume that the NGA pattern, NGA PCO, sorry for the misspelling, refer to the L1 frequency rather than being ionosphere-free L1, L2 PCOs, and this is justified by comparison with Lockheed's PCOs for GPS III satellites, then we can basically make a cross-link from our phase pattern calibrations to the PCOs. And based on that, we were ultimately able to determine frequency-specific PCOs and frequency-specific patterns for all these 4 families of satellites. If we compare the resulting PCOs that we have constructed in that way, and I'm here talking about the ionosphere-free combination because that is the one that we can compare in the IGS, then we see a systematic mismatch. The individual colors refer to the individual blocks, the 2R from left to right, the 2RA, then 2RB and M, 2F and 3 in green. And you see that on the right-hand side, basically, we have a systematic offset of about -12 centimeters if you compare our manufacturer calibrated PCOs with the IGS 20 frame. What is nice, however, is that not only the Block 2F satellites, which were the latest edition, have a very similar offset as the GPS III satellites. Yeah? And also there is, say, the Block 2RB and M satellites are basically partitioned into two groups which have not been identified before, but one group out of that has PCO values that are also consistent with that -10 to 12 centimeter offset. What we have to leave aside, and we could not trace down the reason, is the Block 2RA satellites, which do not match at all. They have been calibrated by Lockheed, but apparently, we know that it was a different calibration facility at a different site, but we don't know what happened. Obviously, the interpretation of the data is wrong here, but we cannot make sense out of the data right now. But the rest seems to fit not too bad. Now, we have used that to put together a file, an antenna model, which we call LMB20, which stands for IGS 20 Aligned Lockheed Martin Boeing Calibration File. What does that file provide you for you? It provides frequency-specific patterns and PCOs for all these satellites that I mentioned before. The patterns are two-dimensional, not Navier angle dependent or boresight angle dependent, but azimuth dependent as well, which hopefully gets a bit more precision into the processing. They are extended up to 20 degrees, which is, say, safely the coverage zone of most space missions, which have to refer to empirical continuations of the IGS pattern so far. And in order to be compatible with the IGS 20, we estimated kind of systematic offsets for all frequencies, block-wise for the 2F and 3 satellites, and satellite-wise for the remaining satellites. So what we have is a two-dimensional pattern with consistent PCOs, consistent with the IGS frame, but frequency-wise and up to 20-degree patterns. That is electronically available as part of an electronic supplement to a publication, and all we can do is encourage its use and testing. We think that it is a fair alternative to the current IGS 20 Antics file. Talking about the scale contribution, we did some further tests. The 12 centimeter offsets for GPS that I mentioned before, relative of the manufacturer offsets relative to IGS 20, would translate or would correspond to a 15 centimeter offset if we would apply to Galileo. And that is surprisingly close to the empirical correction that IGS 20 has done to the manufacturer calibrations that were used in the RECO 3 campaign. Now, if we try to do the following, we use the DTRF20, which is an alternative to ITRF20, which has a known scale inconsistency because it aligns itself to the Galileo and manufacturer calibration and thus has a slight scale offset. If we compare our estimated PCOs from observations relative to, if we estimate PCOs directly for the DTRF20 and compare the manufacturer calibrations against it, then you see the green dots align perfectly with the DTRF-based estimates, while the IGS 20 values have evidently it's a roughly 10 centimeter offset. So that gives us confidence that the manufacturer calibrations that we showed, at least for the GPS IIF and III satellites, are very compatible with the Galileo implied reference scale, and I think it encourages further research into that subject. It gives also more confidence to Galileo, which many people trusted already a priori, but it's good to know that more satellite constellations confirm that results. So in summary, a comprehensive set of manufacturer calibrations has been made available. We have trustworthy manufacturer calibration patterns up to 20 degrees. We needed some creativity. The interpretation of the data sets is far more difficult than for Galileo, unfortunately, but we managed to get that into a new antenna model for the GPS satellites, which we encourage to use. And the scale of that manufacturer calibrations appears to be largely consistent with the Galileo implied scale. Thank you.